Yeah, thank you, Paula, for this kind introduction, and many thanks to all the organizers and the IPAM staff for making this event possible during this turbulent time. So today I want to present some joint work, as you can see, with Michael Burger and Thomas Jung, who are both researchers at the Fraunhofer Institute for Industrial Math in Kaiserslautern, and Elisa Iacomini, who is now a postdoc at Aachen University. So the topic of my talk today will be on the influence of time delays in vehicular traffic. So when we started to think about this subject, we asked ourselves, so which impact do time delays have in macroscopic models that are related to the famous LWR or RZ model? And I think this is a very interesting research topic and research question, also very important for autonomous vehicles. So, okay. So in the next 30 up to 40 minutes, I will guide you through the main findings within these research areas. So I try to give you some motivation and derive the delayed LWR first order delayed model. I will tell you something about the properties and numerical simulation results of this modeling approach. And finally, I also will give you an impression how second order delay models will work. So let's get started. So the framework we have in mind are modeling approaches related on a single road. So we are not talking about networks so far. And on a single road, you know, we can distinguish between microscopic and macroscopic modeling approaches. So microscopic means that agent-based follow the leader models are relying on systems of ordinary differential equations. So the trajectories of each vehicle can be tracked. And the macroscopic approach leads to some fluid dynamic models that are based on conservation laws. So here in the following, I will denote rho as the density of cars at point X and time t, v as the velocity of cars at point X and time t, and f denotes the flux function given as rho times v, also at point X and time t. So as you may know, the fundamental diagram established the relationship between the flux and the density of vehicles given by this short sketch here for as a first impression. Okay, so the LWR model dates back to the 50s, so, and is given as a conservation law, where the main features are that this type of equation is a hyperbolic conservation law, meaning that the total mass has to be preserved. The velocity depends on the density and is typically given by this relation here. So like this relationship. And we all know that this model is easy to implement and very cheap in terms of memory and time, and can be also used on large networks for traffic forecast. But there's also a but. Accelerations are considered to be instantaneous, and traffic is described only at the equilibrium. So we did not expect typical features of traffic dynamics as, for example, the capacity drop or spontaneous congestions like stop and go waves. This you should keep in mind for the rest of the talk. Okay, now we are going to introduce the time delay. And the question we want to answer is there a significant impact of time delays in macroscopic traffic models? So, and to answer this question, we started at the microscopic level, as you can see here. We put the model by Newell, given as x dot, equals some velocity function I of this delta xi t minus the delay or reaction time divided by delta x. So, and this means, as you can see here, this is the description of dynamics for each particle I. And the reaction time is assumed to be positive. So there's no difference here between reaction and delay. So this is a kind of terminology. And delta xi, as you can see here, is meant to be the spacing between vehicle I and vehicle I plus 1. And delta x greater than 0 means that we have some scaling parameter, for example, the average length of a vehicle. So now the goal is to derive a LWR type model with the explicit delay dependence, okay? So we want to see where the delay enters now in the LWR model. And this can be done in the following. So this is not a rigorous proof. This is just a formal way of the derivation of such a delayed equation. So we define the traffic density rho as the inter-vehicle spacing, as you can see here. And the idea of this technique goes back to the paper by Aw-Rascle-Zhang and Materne in the beginning of 2000. So, and now we try to recover most of the steps presented there. So once we have this inter-vehicle spacing, we rewrite now in terms of V this equation and insert it into the macroscopic description I presented before. So this means now that we have the dynamics xi for each of our vehicles given by this relationship relationship of the density description, and we say that this should be now the velocity function of this delayed density. So, and now to link the microscopic and the macroscopic description, we consider the following calculations. So we consider the partial derivative with respect to t of 1 over this inter-vehicle spacing density, and now insert everything we already know. As you can see here, we end up now with the difference between the velocities of this inter-vehicle spacing density divided by delta x. So and now probably you have the idea that this might be a semi-discretization of our problem, and that's definitely true. And the interpretation is now, or the next steps are now to consider the limit process for n to infinity, meaning that we assume a large number of cars. And this leads us to the description you can see here, which is given in Lagrangian coordinates, okay? So this is not the coordinate system we are originally interested in, but this is another description of our model. And meaning now that this y, which occurs in this description, is something like to count the amount of vehicles up to x. And that's why if we would integrate now from minus infinity to x over the density, we would end up in the right coordinate system we are interested in, meaning in the Eulerian coordinate system here. And you see, there's a slight difference compared to the original LWR model here in the flux function, okay? The delay really enters the flux function directly. So if now t would be 0, we fall back to the LWR model. So what does it mean now if we would compare the microscopic versus the macroscopic approach? So I don't want to give you too many details of the discretization here. This is, let's think of some forward discretization in terms of ODEs or discretization of or standard discretization of the LWR model. And let's consider the two special scenarios here. So on the left, you see something called the rarefaction wave, and on the right, you see the shock wave. So let's first stick to the case of rarefaction. You see that we have considered different scenarios like delta x equals 5, 1, or 0.5. And we also compared the delayed LWR versus the undelayed model. And we see that, okay, for the microscopic model and this large spacing, delta x equals 5, there's a difference. And for delta x going to 0, or let's say getting smaller, we see something like a convergence towards the delayed or undelayed model that are quite close in this case. So in the other picture, you observe a completely different behavior. So what you see here is, in the case of a shock, that if the delay here is set, or not the delay, the interspacing is set to 0.5, there occur oscillations in the density. And why? This is due to the model. This is not a numerical issue. If we would go back to the models, we see that the microscopic model is not collision-free. That means it could be the case that if a car reduces the velocity or the velocity totally breaks down, the delay is not able to capture this behavior. So it might be the case that in the wrong mixture of delay and the scaling, interspace scaling, such a behavior can be observed. So I want to further comment on another approach related to the things I've presented so far. So in a paper by Tordeau, Kostasek, Hertie, and Seyfried, they did a similar, they had a similar idea to derive such a delayed model, but the clue is that they also started from the microscopic model 1 I've presented, but they did a Taylor expansion in the argument of W, and then they redo all the calculations we also did. But then they end up, as you can see here, with a different equation. So now the delay does not enter the flux function. It's given more or less as a term on the right-hand side. So we can see here, this is a convection diffusion type equation where this T is something like a scaling of the right-hand side. And if we now compare these two approaches, again, for the rarefaction and the shock wave, we see, of course, especially on the right here, that due to the diffusion of this approach, that this is here, for example, far away from the other two, or from the other two models, the undelayed and the delayed case. So, but let's summarize before we go into the details of the model properties. So we can derive a delayed...
Sorry, Simone, we have a question by Benny. I try to unmute you, Benny.
Okay, on the diffusion, this is an anti-diffusion, right? It always has the negative sign?
Yeah, so this comes from the derivation they did.
Right, so this hints at instabilities, but it wouldn't explain the smearing, right?
Yeah, so the discussion for the discussion on stability or instability, I would refer to the paper where they did a very long and intensive discussion. But this was just we tried to reproduce their numerics, and for a better comparison to our model, which is based on a Lax-Friedrichs type discretization, we also implemented this equation in that way. Might be a reason for the smear out.
But the sign is correct. I mean, in this equation, you always have the square, so it's always pointing in the ill-post direction, right? In the antidiffusive direction. In this.
Yeah.
Okay. Okay.
Can I go ahead?
Yeah, I think so.
Okay. All right. So for the delayed model, we have the following. We have seen that the delay is now inside the flux function, and we also have to prescribe some initial data, which is, as you can see here, defined on the interval from -t to 0, meaning that we need something like a history for the right initial values. This is due to the delay we have included. So, and this is why I put here that the well-posted of the problem needs some initial history function. So, and as I told you, in the limit case of t equals 0, we can recover the classical LWR model. And one further note is that if the delay is not chosen appropriately, the maximum principle can be violated. So meaning that rho can be greater than 1, for example, or rho max in general. Okay, so now I can tell you some of the properties we have investigated. So the first one is now the conservation of mass, which is probably not very surprising and can be directly computed via the integration over the interval AB. We also have the positivity. Let's say we assume we have initial data with non-negative density. Then for the delayed LWR model, the density stays non-negative. This can be proven by some counterexample. And we have the unboundedness, meaning that assume V is monotone decreasing and V of max is 0 for rho max, the maximal density in the classical LWR model, then the delayed first order model has no maximal density rho max. So as I told you, it's allowed that rho can be greater than rho max. And moreover, let me comment on the existence and uniqueness of the solution. This needs to be considered very carefully. So for a slightly different model, Keimer and Pflug did this in a recent contribution. But so far, we were not able to transfer these results to our setting. So numerical discretization and properties. So now the idea is to investigate these properties I've showed you from a numerical viewpoint, meaning we have to introduce a grid in space and time, and we need to introduce discretized variables as done here. And remember, so we have a CFL condition, a stability conditions we have to satisfy. And if we would now apply some Lax-Friedrichs method as it's written here, you can think of how this method can be applied in the delayed setting. So, and more or less, this can be done in a straightforward way, and this is what we call altered Lax-Friedrichs method. And you see here the difference is that the flux is now including a delay, so it's slightly different from the typical or classical Lax-Friedrichs method. And we have a few things to ensure. So first of all, the delay is greater than delta t to treat the delay. And t delta should be the number of steps that make up the time delay t. And we identify the flux given in this notation as rho in the discretized version times the velocity with regard to this delayed expression. And for the well-posedness of the discrete problem, we also have to provide initial history function, as I told you before, meaning that we have to keep in mind that we need a definition on the interval minus t up to 0. So, and the properties we are now going to investigate are, first of all, the conservation again. So on the discrete level, we have to investigate the discretization I showed you before. And the conservation is ensured by this expression, meaning going back to the discretization, then we see we have a summation of these guys here, leading to this term on the right. And we see here that this is something like a telescope sum, and which will vanish in our calculations. So this gives us then the conservation of mass. And the positivity, we have to, for the positivity, we have to guarantee this inequality here. And what's really interesting at this point, that we need now to ensure a different kind of CFL condition. So this is not the classical one, but due to the calculation of this positivity result, we ended up with this CFL condition, as you can see here. So, and this is now something probably not straightforward, but you see that we have to take care of the delay also in the CFL condition. And we also assume that now the velocity v of rho is bounded by the maximum we also have to include in the CFL condition. So, and to give you an impression what would happen if we don't work with this CFL condition, we again consider the rarefaction and the shock wave. So in the first row, you see the rarefaction, and in blue you see the delayed LWR model without the new CFL condition, so with the classical one. And you see here these silly oscillations. And if you would apply now the CFL condition we have derived, you see we are in a fine setting again. And this is also true for the shock wave here in the second row. So there's a really strong need to work with this new appropriate CFL condition. So let's talk about two other bounds, the L infinity and the TV bound. So for the L infinity bound, we need that we try to find some upper bound, but due to the positivity we already have, we can compute more or less directly this upper bound for the L infinity. And for the TV, we distinguish between the TV bound in space and in time. And due to some indices shift, we are able to derive both. So these are some longer calculations, which I will not present here in detail. So far, we have some estimates, and now we can go ahead and discuss numerical tests for this delayed model. And starting from some empirical observations in a paper by Cristignani and Iacomini, we assume the velocity function as v of rho, and now three cases, v max, some alpha times 1 over rho minus 1 over rho c case, and the zero case. So alpha in this special situation should be a parameter. And you see there are actually two density thresholds. So one is rho c, and this represents the so-called safe distance at the macroscopic level. And the other one, rho f, represents the distance until vehicles influence each other. And as we will see in a few minutes, there are special choices for these two thresholds, but let me mention that if you choose the parameter alpha in a bad way, this velocity function could be discontinuous. So for the scenarios I will introduce now, we have chosen the following setting. So we have some unit space interval, some discretization delta x of this type. We also consider periodic boundary conditions, and delta t is chosen that the new CFL condition is satisfied, and the threshold I've already mentioned are here 0.75 and 0.2, and this is taken from a paper by Balzotti and Iacomini, which is based on some real data estimations. And for simplicity, we choose the delay to be a multiple of delta t, as you can see here. So the first picture compares now the LWR versus the delayed LWR model. And the idea is to present some perturbation in the initial data, as you can see here. And we have fixed a delay of this type. Then what would happen? So on the left, you can see the LWR model, and on the right, you see the delayed LWR model. And the density evolution shows that the LWR model smears out of the perturbations while the delayed LWR model preserves them. Yeah? Here you see really this kind of perturbation waves, and here we see that after a short time, the density gets constant. So this is one of the first big differences we can observe while considering perturbations in the initial data. So if you go into the details, then you will see that the crucial role is the choice of the delay. So if the delay is too small, we are very close to the original LWR model, meaning that we really recover a situation similar to the LWR model. You see, okay, here are the perturbations still there, but they try to smear out. And if you look on the right, so there's now the density plotted over X for a fixed time, you see nearly a constant behavior again. So small delays are not the best choice, but if the delay is too large, it's also no good. So, and again, we consider this perturbed initial data, and you see for a larger delay, like given here, after a while, the density increases and exceeds rho max, which was chosen to be 1. So the hypotheses are no longer satisfied and the density starts to oscillate. So what can we also say about stop and go waves in the delayed model? So our definition of a stop and go wave is like stop and go waves are a typical feature of congested traffic, and a stop and go wave is detected when vehicles stop and restart without any apparent reason, generating a wave that travels backward with respect to the car's trajectory. So, and stop and go waves are one of the main reasons for accidents, longer travel times, high fuel consumption, and pollution. And when I produced these slides, I wanted to show you a video, but this video has been shown so often during this conference now. That's why I tried to skip it here, but I want to mention that many people in the audience participated to this video, and I want to give you the link if you're interested in, and you will see one of the main things I try to summarize here. So what does it mean for the delayed model when considering stop and go waves? So let me give you the details. So if we would start with the density profile given here, and a delay of this type, and then do the simulation, then we observe the stop and go wave at the final time, which was 3.5 here in a well-defined sense. So I can tell you that well-defined means this is now the reference by Flynn et al. And I guess also Benny Seibold contributed here. So, and we end up with a stop and go wave of this type for the delayed model when we start with this initial data here and periodic boundary conditions. So this is now the real difference to the LWR model. The delayed model is able to reproduce stop and go waves. And we also see that the triggering of stop and go waves can be also done. So now for the initial data, as we see here, so there's a higher density in a very small area on the x-axis and some lower density elsewhere. Then we observe that the initial perturbation really increases and moves backward as time increases. So far, we were very happy with these results, but we also tried to investigate now second-order traffic models with the same kind of delay or the same idea where the delay can enter the models. And this is something I want to show you now. What would happen if we now go one step further to second-order traffic models and introduce a time delay there? And this is what I call a follow-up question. So what do we observe in second-order delayed models? So starting now from the model by Gatzes, Hermann, and Rothery in the 60s, so which is now second order, meaning that we have one equation for the location of vehicles and one equation for the velocity of vehicles. So, and you see here, this is different to the one I presented before. So now we also have to take into account the difference between the velocity, including the delay of vehicle I plus 1 and I. And here again, we have the difference between the locations of these two, and we have some scaling gamma plus 1. Again, we consider a uniform delay and model constants C and gamma, as I told you, where the C is composed of some reference velocity or reference speed times some delta x to the power gamma. And using this type of equations, though, we can do now several approaches to derive second order delayed models. So I'm going to present only one approach. There are other ones. So the one approach that is directly related to the ideas I presented for the first order model is now we can redo the calculations in the sense of scaling and using Lagrangian variables to describe the delayed system. And then we end up with this type of Aw-Rascle-Zhang equations. So what do we see, or what's our final result? If we would neglect the right-hand side here, this Q, we really would be in the setting of Aw-Rascle-Zhang, okay? But now you see that we have some source term entering the second equation for the velocity here, and the source term is given by this description here, where also the delay enters into the problem. So now the delay is given on the right-hand side. And if you would do other derivations of this Aw-Rascle-Zhang delay type equations, you will always get that the delay enters the right-hand side in the second equation. So what does it mean? I decided here to present one result, namely the data fitting approach for now the second order delayed model. So what we did is inspired by the work of Van Hertie and Seibold to take some data from the Minnesota Department of Transportation, as you can see here, and then do a parameter fit. So again, you see first in this picture, the fundamental relation between density and flow. And we have a lot of data points. And what we aim to do now is to fit that fundamental diagram using this Q of rho function and doing the fit in a least square sense. So, so this is something we did, and what we can see here is in red, given the approximation we can achieve, and we see here in the beginning, in the low density regime, there's something like a linear relationship, and in the higher density regime, we see a spread of data, and therefore the second order approach is a reasonable one. So, again, assuming that we can apply some Lax-Friedrichs type discretization for the delayed RZ model, we observe the following results. So we took a road segment without on and off ramps, and we consider a time interval as given here on a usual work day. So then we observe in the density and the flow the reference solution, the RZ solution, and the RSD solution, meaning that RSD is the shortcut for our delayed RZ model. We can observe that the classical RZ model tends to avoid deviations, while the RSD or the delayed RZ model has stronger peaks, okay? We also observe that both models, the RZ and the delayed RZ, are, let's say, shifted somehow to the real data. But this is something Van Hertie and Seibold also observed. So this is nothing new. So this is modulo, or this can be seen modulo a time shift given by this reference data. So I have no clear explanation for that. So what we also did is we measured the error between the real data and the simulated data via the error measures, via one error measure presented also in this work by Van Hertie and Seibold. given by this expression here. And we could see that the RZ model will lead to an error of 0.64 and so on, while the RSD model leads to a slightly lower error given by the 0.60 and so on. So far, we were very happy to see that the delayed RSZ model is also able to capture this real-world phenomena. So let me conclude and talk about future perspectives. So as we have seen here, we have introduced new delayed macroscopic traffic models, and I tried to point out similarities and differences to the underlaid versions of these models. We have proposed an altered Lax-Friedrichs type method to compute the numerical solutions. And we have also seen that the LWR delayed model is able to reproduce stop and go waves, while the delayed RSZ model performs well regarding real data. And as a future perspective, we are very interested in advanced parameter estimation techniques to get a better feeling about all the parameters involved in traffic flow models. And we are also interested in the inclusion of stochastic events, as for example, accidents for a better route planning. So my talk was based on the following references I've listed here and supported by the German Research Foundation. And let me thank for listening.